Yeah, so this is a really exciting opportunity for me to talk about C++ for scientific software, and I guess specifically modern flavors of C++. I'm research scientist at CCQ working on one of the major software packages, and I'm using C++ every day in and out, and kind of trying to stay up with the various developments that are happening and the new tools that are coming out. So if you have any questions also regarding other aspects of C++, just let me know and we can have a chat. So why is there even such a thing as modern C++, right? Like, what is old C++, and why is there a language evolution? Of course, the language has been around, as many of you know, for a good number of years now. Actually, it was released initially, the first version, C with classes, in 1985. It had a different name back then, by Bjarne Strostrup, and was ISO standardized only several years after. So it was standardized in 1998, which defined what many of you may know as the C++ 98 standard. And that one stuck around for quite a while, until the C++ community decided to more regularly update the standard in a 3-year cycle. That started in 2011. And also defined the C++ 11 standard, that was a very, very big standard, in fact, that contained a lot of things and improvements in the language. And since then, yes, every 3 years, we got a new addendum to the standard that generally, of course, everything, all the changes that were brought in were keeping things backward compatible against previous codes, at least to a very, very large extent, backward compatible. But not just adding components to make the language more complex, but generally to allow you to write things in a simpler and more expressive way. Meaning that there is, for many things in C++, more complicated ways of writing something and easier ways of writing something. Meaning that also when you engage with the language and you learn it, it's pretty important to focus on the right material to learn it and to use updated and modern material to learn the language. And I'm going to give some recommendations on what material I think is going to be useful later in the talk. But I will go into some code examples before we do that. So the language directions, I think these are some general directions in which the language has evolved. Syntax has generally become a lot more Pythonic, Python-like. You will see that in various examples that I'm going to be showing. Those of you that have used Python before, some of the syntax looks almost one-to-one, except for the additional specification of types, of course, because Python is not statically typed. Generic or template programming has become a lot easier with many of the additions to the language. I will also show some examples here. And one can now make explicit decisions about doing certain things actually at compile time, and then only and other things at runtime. You can make explicit decisions between the two things through a number of keywords that were introduced. C++ or modern C++ really moves away from C-style programming, where you use raw pointers. In everyday programming, I barely use them at all. And if ever, then using smart pointers or more safe pointers that come with the standard library is actually good practice, and we do that also. And I'm going to be covering some of the topics that are shown here on the right side. Some of you may be familiar, or those that have seen C++, many may be familiar with the auto keyword that I'm going to start with. And then I'm going to go very quickly actually into some fairly recent features that were introduced. I'm showing here ranges, coroutines, and concepts, which are really 3 of the big topics that were introduced in the C++ 20 standard. I'm just going to be able to scratch the surface of these things, but very happy to have maybe potentially follow-up events to this one, where we can go a bit more in depth into one of these different directions. And then the other topics here, I'm also going to touch on, specifically the compile time programming part towards the end. So let's start with auto, the auto keyword, and what you can do with it and how it facilitates the language. I hope the code samples are all good, readable well in the back. Try to make them as big as possible. Yes, the auto keyword allows you to deduce, well, generally C++ is a statically typed language, meaning every variable that you define has a declared type that you can figure out, that you can look at. It hands over to the compiler the work of deducing the type for a given variable. That will, of course, only work in the cases where it's non-ambiguous, right? In some cases, it will not be able to do that, but in many, many cases, it will do that. Here I'm showing some use cases of the auto keyword in variable declarations. So you could, in this case, just simply define a variable x that holds the value 5.0, and the compiler will immediately know that this is a double, right? You can use the auto keyword also to write what I like a lot, actually, a more Python-style declaration syntax, where you don't use the type on the left side. You just write auto v, and you use the type on the right side to write something like v is a vector of these values, right? Which I find more readable in code generally, as opposed to the more common older C syntax where it's more interleaved. You can declare or you can auto-deduce the type from different expressions that can be much more complicated expressions where you don't actually care exactly about the intermediate type. You just care about the result and you want to pass it on or immediately use it. And of course, also when you call functions, the return type may sometimes be clear from the local context. You can just auto-deduce it in the way there as well. You can just use it for variable declarations, but you can also use it in defining functions. We're seeing here a dot function that effectively takes two vector-like objects and creates the dot product in the way that you would expect. It multiplies the first two elements and then adds to that the product of all the remaining elements and just returns that result. And this function has auto in a number of places. As you can see, right, the first thing that we are declaring as auto here is the return type. So that's going to be auto-deduced depending on what comes in. The compiler will know what comes out, right? Meaning this function is actually applicable to a lot of different types because we also use the auto keyword for the input. This is going to auto-deduce the input for A and B, and they don't even have to necessarily be the same type. There could be a different type for A and for B. If you were to write all the overloads for that function explicitly in old C++, even just for 3 types, this is going to blow up very quickly, right? Thinking about a function with 3 arguments, it gets even worse. So that combinatorial explosion you can completely avoid with this auto syntax here, and the function is going to apply for multiple cases. Some of you may recognize this syntax is very effectively does the same thing as the old template type style syntax, where you define template type name A, type name B, and then you use A and B here in the definition. It's just a more concise way of writing it. Yes, there's a question. Can you use the mic? Can you use your seat mic?
Yeah. So how does it determine what a float versus a double? Like, is there a set of rules in the standard?
There is a set of promotion rules. If you multiply a double with an integer, for example, you're going to get a double back. If you multiply a double with a float, you're going to get a double back. Effectively, you're going to try to use the more precise type in these kind of operations.
And if there's situations where it's a little unclear?
Yeah, it will tell you. The compiler will complain if it cannot deduce the type with auto. And it will tell you there is an ambiguity, and it will give you an error message for that. Yeah.
Thank you.
Yes. Can I ask what the I thought you had an off by 1 error, but the reason you're starting at 1 is because you've used the first calculation to declare the type. It's a kind of sneaky trick to get the type out. But is there another idiomatic way to set up, let's say I wanted to say auto res equals 0, but I didn't know what type of 0 it was.
Yeah.
And then you accumulate it.
Yes, you can do that.
Because I don't want code duplication about A times B.
Yeah.
Is there a way to do that?
Yeah, there is a way to effectively take the value type of the A and the value type of the B and deduce the value type of the product of the two. there is an expression that you can write in order to get that out, and then just define the 0 based on that type. And then you could start at 0 also.
Is there a case where the first one is ambiguous and the second template version is not? They're always the
syntactically
same.
equivalent.
Yeah.
This one is syntactically equivalent to this one, at least in this formulation, right? Not syntactically, but under the hood when the compiler looks at things. Very good. So much on the auto keyword. We're going to see it a lot more anyways throughout the talk, because there is more.
I was
Another
just,
question.
okay, so I like auto, makes writing code a lot faster, but one of the problems I have is code readability. A lot of times, like
Yes.
if you have something that's outputting, you have a generator that outputs an object and you don't necessarily know what that object is at the end of the day.
Yeah.
How do you handle that problem in the actual like writing of the code for people to use, like modifying the code? Because a lot of times like Python is going in the other direction of more like type definitions.
I think one should prioritize code readability over use of auto. I'm not saying that use auto everywhere that you can use it.
Mm-hmm.
In some cases, when you're using modern IDEs, it will actually be able to tell you locally when you're using a function, what is the type going to be deduced as. So you can use that IDE information. It's going to tell you what the type is, but someone that doesn't have that set up in this way, for example, is not going to have that information clearly. So it should be clear from the local context of the code that you're writing what the types should be, such that you can omit them. And also for int, for example, I don't usually use auto myself unless I know there may be other integer types coming in or something like this, right? If the type has a short name and it's clearly defined, write it down. Why would you use auto there, right? It's more about not having to write out long types where it's clear anyways what they are. Okay, maybe we should move on. I think we have a good number of examples left. And I want you to also be able to attend the reception. Yes, so I'm moving to a different topic, which also is related to type deduction by the compiler, and that is the so-called CTAD, or class template argument deduction, which is a complicated name for actually a fairly simple thing. Many of you know the vector type already, right? You typically you can define the type of which you have a vector, which goes in the angle brackets behind it. The compiler can also deduce that in many cases, right? Because if you define to construct a vector from 1 to 3, it's pretty obvious that this is supposed to be an integer vector, and you can just neglect that, which also makes code a lot more concise in many cases. This also applies for your own types. So if you define a type which depends on types, which is a class template, in this case, we have like a point to D, which has a value type and an X and a Y, right? In this case, you can simply define P1 and P2 by passing in, for example, integers or floats, and it will automatically know in one case you get the integer version, in one case you get the double version. Yes.
Could I use auto instead of value type inside the struct?
No, I don't think so.
Why?
Not allowed by the syntax. Maybe the language will move there, but I think, no, you have to be explicit. You can't, you can only do it in declarations, not in declarations, only in definitions you can use auto. And if you just write auto I, comma, or semicolon, it has to be able, as the compiler goes through the class, it has to be able to infer for everything what the respective type is. Okay, very good. That's what I wanted to say on the, I think this is another nice syntactic sugar simplification of C++ that makes things just easier to read and more Pythonic. Another one that goes in that direction are the so-called structured bindings, right? When you have tuple-like elements that could be a pair, a tuple, an STD array of fixed size, many of these things, often you need to decompose it into its elements, right? And the compiler knows how big the thing is, right? All these things, pair, tuple, and so on, they have a compile time size. And the compiler can just decompose the things, right? You could, in this case, just simply write auto, and then in brackets, this is the syntax you need to use, and that always goes with auto. A comma B equals my pair. And in this case, it's going to generate you a copy of the elements inside. Yeah. You can also tie the values of the my pair into existing variables by just using references on the left-hand side. That would be with the std tie, for example. And this has another very nice use case because you can now easily return multiple arguments from a function, right? So you have a function that needs to return multiple things. You just return a tuple of these guys. And then on the call side, you just effectively write something like this. That makes it quite concise in many cases, even if maybe in some cases you don't necessarily need the C and just the A and the B. It's okay. Yeah.
So, I mean, one of the reasons, I'm an old style C programmer. So for me, the arrays that are passed out are done through an argument, are just pointers in the argument list.
Yes.
And that way, it's the user's job to pre-allocate. And that gives you a certain speed advantage because then you write into a pre-allocated array. Here, does this allocate ABC afresh each time? I mean, can you get that performance of writing into existing arrays, or is that just is this just not, you won't get that performance?
Let's say that you create a big object inside the function. What this will actually do, the compiler does what is called return value optimization, where it actually will take the thing that you created inside and move it to the outside, which effectively doesn't make a copy of the thing that you're moving outside. If you wanted to say at the very start of your program, allocate a big chunk of memory and continuously use that, you have to, of course, pass that into your function because your function internally doesn't necessarily know about it. But at least at the level of the objects and the big objects that potentially get created here, those will be not copied, but moved. This is called move semantics within C++. Yeah. More questions? No. Good. Another nicety, Python-like change. Printing has been revised quite a bit. Many of you may know printf. And in C++, that was changed into streams, std cout, std endline, all these things, which is actually a very clunky syntax when you have many things that you want to print out. There is now std format and std print, which are better and safer versions of printf in some sense. They're extendable. You can define for your own types what it means to print something. Std format will generate for you a string, right? Given some format string here, where you can give here, the arguments are going to go in there, and you can also give things such as precision for doubles and stuff like that, that you can actually put in there, and then you give the arguments there. Or you can directly print to cout. Yeah.
But you don't yet have a syntax for directly interpolating the variable in there, like hello, comma.
There's no f strings if you want to,
Yeah.
Unfortunately not.
26.
Python f strings are where you effectively, inside the bracket, you would write name. FMT has a way for it. Okay, so the library that I'm mentioning here at the bottom was actually before this was brought into the standard libraries, everyone was using this one, which because it had exactly the same API, but was also more powerful. Apparently has a way to directly put that in. I haven't used that part.
Yeah, I used that. And for some reason, somebody didn't standardize it.
It would be very nice to have that, yes.
Yeah, maybe next time.
But it's very easy to use. I think this is pure header, in fact. So it's very easy to just use that as an additional dependency in your program. Okay, so much for the printing. For loops have also been, there is another question.
Actually, something I've just never thought about before. When you say auto name,
yeah,
is that going to be like a C style string, or will that be okay?
Unless you use, there's also string literals where you append this guy with an S, this thing, and then it becomes a std string. Yeah, there's string literals you can use for that. Very good. For loops or range-based for loops. This is also very Pythonic, right? If you have something that you can iterate over, like an std vector, in this case, just a vector of cars, you can write also with auto, just the syntax auto C in V. And the in is effectively the colon here that you have to use, right? Which makes it very easy. In this case, the C is going to be a copy. Of course, this could be optimized away, but you can also use the ref sign to make it a reference to the elements inside the vector, and that also allows you to potentially change things, right? In this case, you're kind of zing out the elements of that vector. Yeah. This is actually compatible with the structured bindings we saw before. So if you have like a list of pairs or something like that, right? Or you have a map, for example, map of car and int, something like this, then you can do for auto key value in M and just do something with that. And you immediately have the key and the value. That makes it also quite concise. And that almost looks like Python code, except for the types that are there, right? So yeah. A lot more has been happening on ranges and loops and writing of loops. There was a whole TS, and that was all merged in C++20. Some parts were delayed to C++23 and are now being added in. But the whole range TS allows the whole writing of loops and changing ranges a lot easier. You had another question?
Maybe it gets answered with this. I was going to ask, how do you get in the index? Like, I have many applications that I need to know, let's say the key value pair, but I also want the index of
you can,
where
yeah,
in
I
the
can
map
show,
that
I will
okay.
address that, yeah. In this case, if you just want a range of integers, unfortunately, it shows what I believe is a pretty bad name, but it's called iota. But that thing exists and is effectively the integer range. In this case, going from 0 to 6 exclusively, and this prints out what you would expect it to. Actually, this should start at 0, and this is a slight error. Right, going from 0 to 5 is what this would do. And this is actually going to be lazy in the sense that only when you start pulling out the values are they actually created. So if you make a gigantic iota view, this thing is actually super tiny in memory, right? This is lazy evaluation that's happening there. A slightly more complicated example, and that addresses what you were asking, is if you want to count integers on something. Unfortunately, this doesn't exist yet on Clang. This exists in GCC 13. Everything else that I'm showing on my slides actually compiles with Clang version 13 that was released some 4 weeks ago, I think. But all the other examples you can actually use today in your research code. If you're just using an up-to-date compiler, which I can point you to a simple installation script. I'm sure the new modules are also going to contain a more recent version of Clang. And I also have a build script that makes it super easy if you want to just have a recent version of Clang available to yourself. Yeah, and this is going to print what you would expect, right? IC. This is just going to enumerate the characters that you have there, and you get this output. There's another question.
Yeah, can you combine that with a map? So like instead of C, you're mapping like a tuple or something?
Yeah, you can do. I don't think you can do that where you have multiple decompositions, where you have like a structured bindings inside a structured bindings. That kind of a syntax you can't do. No. That you have to do in 2 lines effectively then. But these things are super composable, and that's really what makes them very powerful. This is a more complicated example, and I'll let you quickly, or let you read this first before going through it. It takes a brief moment to consume. So these, because they are lazy, these things can be infinite, right? Iota 0 is just the range of all integers starting at 0. If you were to loop over it, it would be an infinite loop. And then we have a second vector, that's the vector of cars. And the first thing we want to do is we want to zip the 2 together, which now makes it a vector of pairs, right? That's what the first thing is going to do. The next thing is just going to drop the first 2 elements of that new sequence. This is kind of a piping syntax, like in Bash almost, right? Which allows you to compose these things super easily and makes it very powerful. And you could actually inject STL algorithms. Many of them are also in the STL ranges syntax. You could interleave them in between to say something like square the elements or something like this. And then take 3 is just going to take 3 elements out of whatever remains, because we need to have a finite sequence. Actually, the zip right here is going to take the minimum of the 2 sizes already, as far the way I think it works. And that will give you what you expect. Yes, there are some questions.
To perform like near the boundaries of a signed integer or something like that. Like you say it's infinite, but with a fixed size type, eventually you're going to run out of bits, right?
Yes, you're going to get an integer overflow probably in that case, right? That should be detectable though in your program.
Yeah.
If you're really running over the boundary, you can just use tools that are going to tell you that that just happened.
Sorry, I hope this doesn't sound like a critique, but I'm just trying to understand what the advantage of thinking this way is.
Okay.
In terms of readability, that's all. I mean, you know, I would much prefer to read a for loop that says go from, you know, well, here maybe it's because it's a contrived example, but like to do the thing in a concrete fashion, like in a programmatic fashion rather than a abstract fashion in some way. And I just, is it that you get to generalize later when all of for different objects and stuff? Is that kind of like where this is heading maybe?
Well, the first approximate, this is a fairly simple example where all the objects are something that you could potentially just index into, and then you just do an integer range. But there is more complicated things that you could iterate over, right? Think of it maybe more in that way. And in all these cases, the syntax is going to make things a lot easier to write, I would say. I mean, this may be a bit, it's a slide example, right? In some way, the types that are really going into this are pretty simple types, but in a more sophisticated research code, the things you're looping over may be whatever big objects that you have inside something that you can iterate over. Yeah.
Also, for that stuff, isn't it the case that for all the parallel fors, etc., they kind of force you into using that instead of using standard int I?
Yeah, I mean, yes, if you want to start using the fact that many of the STL algorithms can be executed sequentially, like in Perl, right? Many of the STL algorithms have been extended. I think this was mentioned this morning, right? In ways that you can automatically do threading on them in a sequenced way or an unsequenced way. And I think there you quickly run into problems if you try to do it the standard way. Yeah. Good, let's move on. Talking about Lambda functions next, which is also a very useful feature that probably a good number of you have seen that has been around in the language for some time now. These are anonymous functions that you can just define inside another function and use them immediately, right? This is a very typical syntax that you would see. And this first bracket here is to decide what from the outside world do you want to see. It's the captcha list. In this case, it's empty because we just need the argument to the function, which is an integer I. In this case, we're just simply raising it by 1. And then we can immediately call that function, and you would expect what you get what you expect in this case, which is going to be 3. And if you compare that against the Python syntax, it's in fact very similar, except again for the additional type information that you have to put down. And Python is not very explicit about what you see from the outside, but there's no captcha list in that sense. Python makes that a lot more ambiguous, I think. And I find it actually quite nice that we're being very explicit in C++ about what do you bring into your Lambda and what do you not see inside your Lambda. More complicated example, or what is a use case where you would actually want to now define and use a Lambda function potentially. This is right here a function that takes a very naive approach to integrating it in the interval between 0 and 1, just evaluating the function on a given set of nodes and multiplying it with a fixed weight, 0.1 in this case. And we don't know what the type is going to be of that function here. Lambda functions have, in fact, types that you don't actually ever want to look at. They should always be declared with auto. And you don't want to specify the type here, so you just take auto f as an argument to that integrator, and yeah, and then you can call it, for example, with standard functions like the cosine, or with your own version where you have a cosine of 2x, and you can integrate these functions between 0 and 1. A more complicated example may be where you want to integrate a function that has 2 arguments. There, what you would want to do is you would want to fix one of the arguments, right? You want to curry that additional argument. For example, when you take the function that raises y to the x. Nope. You will want to use some variable from the outside, and you need to capture it. In this case, we want to capture that first result that we have calculated here. We capture it by copy in the captcha list. And then we have a function that only depends on y, but inside uses R2. And we can also integrate that. Yeah.
Is the ellipsis notation actually valid in that, or is that just your notation up on the screen?
Ellipsis notation.
Do 3.
Sorry, no, that won't combine.
Okay.
No, that won't combine in this case. Yes. Exactly. Yeah. So as I said, this thing you want to capture first. Another case where the lambdas really shine is in combination with the algorithms that I mentioned before. There is a big bunch of algorithms, generic algorithms implemented in the standard library, in the so-called standard template library. This is what the abbreviation stands for, STL. You may hear every now and then. And what the STL implements is a set of containers. We have already seen vector. There's a good number of other ones, and a set of algorithms. And these algorithms, most of them are actually applicable to most of the containers on the left-hand side. And this is done not by implementing every algorithm for every container in a multiplicative fashion, but by doing an abstraction layer in between, which is the so-called iterator interface, because all these things can be looped over, right? You can do for auto X in C for all these guys. They all have a beginning, they all have an end, and then the algorithms are implemented based on that interface, which makes it much more manageable to implement all the algorithms for all the container types that you may get. The container types, this is a list of, I think a complete list of all the containers that exist. CPP reference is gonna list them out for you. I think the ones that you should care about in probably 95% of the cases are the top two. There's a statically sized contiguous array, STD array. This thing is always going to live on the stack inside the function memory. When you call a function, this is going to be initialized there. And STD vector, which is always going to do a heap allocation, which is going to call malloc and create memory somewhere which is not in the main call stack. But that allows it to be dynamically sized, and you can also change the size of this guy. Yeah. Questions? Yes, there's a question.
So for the array template or container,
Yes.
Does that do bounds checking if it's
You can,
stack allocated?
yes.
Is it automatic, or does it?
It's not automatic. For the STD vector, you mean?
Yeah.
No. In this case, if you wanted to always bounds check, you have to use .at as opposed to bracket. Yeah. So I mentioned these two cover most of the use cases. So the algorithms, I'm definitely not going to be able to cover all of them. This is kind of a list, and I don't think this is even all of them. If you go to the CPP reference page, the number of algorithms that exist there is quite enormous. And they have been also extended recently, actually, in many directions. One is in the direction of parallel execution. You have heard about that this morning. Also in a way that it actually allows you to do some of these things on the GPU. And then with the range TS, they have also become a lot more composable in the way that we have seen before. You can also now pipe a sequence into an algorithm and then pipe it into another algorithm, for example. And a simple example for that would be, a very simple example for that would be sort. I'm going to be using here the most modern syntax that uses the ranges version of the algorithms in this case, where you don't have to, where you can just simply pass v into sort, and it's going to in place edit it. Unfortunately, due to historic reasons, you have to use a slightly longer namespace specification here, std ranges sort, but you can do an alias for this. You could just change std ranges into stdr or something like that if you use that a lot in your program, just to make it a bit more concise in all the cases where you want to use that. Let's look at a more complicated example. Those that have seen the Cywa modern C++ may recognize this one, but I think it's a very nice and intriguing example. So we have a vector of integers in this case. And what we want to find is we want to find the order of traversal from the smallest to the largest. So going from 1 to 2 to 3 to 4 to 5 to 6. So what is the order of integers such that you index in order of the elements? So that you think for a brief moment what you would do, maybe in another language potentially, in order to solve that problem and to find that, to generate the list of indices that takes you from the smallest to the largest in this case. You have an idea?
That you should sort, I mean, do whatever your sort algorithm is, but then act on another array. Every time you do those swaps, you act on another array, and then you invert that list at the end. I mean, it's a little painful. Is that what you're asking us to
Yeah, you don't. I don't think you even need to do the inversion, but that's almost what it's almost exactly what I'm writing down here.
Okay.
So the first thing is to just generate a new vector, which just contained integers 0 to n. Right. This is what this iota is going to do. It's going to fill this first vector with the elements 0, 1, 2, 3 to n minus 1. And now you're doing a custom sort on the L as opposed to the first guy. And you're doing this custom sort on the L in a way that two integers I and j compare less if and only if v of I is less than v of j. Just letting you consume that for a moment. It takes a moment to think about. Say again. Vector minus 1? No. Is it? Okay. That's by chance, I think. I don't think that's, yeah. Yeah, that part, yes, but that it's really the first, no, that you subtract 1 from this guy to get this guy is, I think, by chance just now. Okay, I think this is a nice way, but you can do many more things and you can customize many of these algorithms to do what you want to do. Some other additions to the, in this case, standard library that are very useful, I think, in a scientific context are view types that have been added. STD span, I think was also mentioned this morning, is a view type on existing memory. So you, in this case, we're just initializing an array of a fixed size. And as you can see here, the class template argument deduction can also figure out the rank of the array automatically, right? So you don't even need to specify either of the two template arguments here. And then the span, we're creating it from the 4 to the 2, right? This is effectively the beginning of the array plus 1, and then we take 3 elements. This is the way that we're creating the span here. So it's just viewing a small subsection of that larger array. And then, yeah, when you just print out 0, the 0th element of that segment, you would get 4 as expected. And you can sort the segment, but it's just going to sort the middle part of the existing array. So if you print out the array afterwards, you actually mutated it and you shuffled around the middle part, right? Which can be quite useful if you want to act on a larger chunk of data and you're just viewing like a smaller piece of it, make some alterations there. That's why these things are super useful.
Functional bounds checking.
I think in the same way. I think the API is very similar to STD vector, but I'm not. It knows the size, right? I think it should have, Olivier, doesn't it? Check it. CPP reference is your answer. Yes, I would expect it, but can't guarantee it right now. Okay. This thing exists not just in 1D. Since C++23, we have a m-dimensional version of this guy. So there is now a multi-dimensional array view, which you can access into with multiple arguments in the way that you would expect a multi-dimensional array to work. Just you have to take care of creating the memory, right? So we're creating a vector here with components, with integers from 1 to 8. And then we can create a span, which is a multi-dimensional array view on that data, which is just a reshape. It's a 2x4 array on the same data, effectively. Yes, there's a question.
So just to be clear, the comma operator, quote unquote, has officially been removed, and it, multi-dimensional indexing is now a thing.
Yes. Okay. That was for those that know this detail. Previously, the bracket operator in C++ could only take a single argument, and that was actually constrained by the compiler. This has been removed now, and you can now define bracket operators with multiple arguments and leave out all these nasty workarounds in order to make it happen. Yeah.
Is there a flag where I can have it have it be column major, like the way the matrices should be? And
I think you
it's row
can.
major, right?
This thing is heavily templated, and I think it's matching. So this is effectively the view type, which is the predecessor to the MD array, which is actually going to take care of also creating the memory for you. And that one is very, very flexible, and is actually what is used inside in the Cocos library, and came out of that and is now being standardized. Yeah, so you can make left and right. Okay, so you can make that choice. Yeah, very good. 20 minutes left. I think that should be okay. Yeah, and you can mutate. Of course, if you know change any value inside that view, you're going to mutate the original data, right? So if you write 42 into the 0, 0 element, the V is also going to have a changed value inside of it. So these are really views; they don't own the data. Yeah. Okay. I think this brings us more to deeper language features that have been added in C++ 20 specifically. I want to start with coroutines. Who has heard about this before? Because it's not just a C++ thing. It's a thing that has been around for several years. I think COBOL was one of the first languages to introduce it based on what I found in the 60s, but has not existed in C++. And I think is also not fully supported in many other languages. But let's look at an example here. So this function right now is going to calculate a Fibonacci number, the nth Fibonacci number. This is an implementation that's going to calculate that for you in the way that you would expect. But the specific thing for Fibonacci is you have a state, right? And you have to kind of store the state in order to calculate the next elements. You have to remember the state and add effectively A to B and update the A with the B value. This is the way that the calculation of the Fibonacci sequence works. And this is just an example that should now stand for a fairly complicated scientific calculation where you have a lot of intermediate results that you calculate and that you may want to keep around if you ever want to continue calculating the next element, right? This is a very common thing when we set up scientific codes. So how can we avoid recalculating it, but still get out the value at an earlier point and then maybe return? And wouldn't it be nice if we could just keep the function around and go back to it at some point? Kind of keep the function alive, return from it, and then go back to the function. And this is really what coroutines do for you. They elevate the idea of what a function is to a function that you can pause and, or that you can pause and resume at some point. So very similar to what in Python you can do with the yield keyword. In C++, you can co-yield the result here, which is your B, which allows you to return that value. It's not the exact correct syntax. This code right here on the right side is not going to compile because what this function now is going to return for you is not an integer, but a generator of integers, because you need to be able to have a handle to go back into it. If you were just returning the integer, how would you jump back into the function? You also need the handle to go back into it. So the correct syntax here, and this is unfortunately not yet possible with the standard library, but thankfully with one of the support libraries that exactly matches the standard syntax. So once this enters the standard library, all you have to do in the code that I'm showing here is change the CPP coro into STD, and it's going to work exactly the same way. So the way that this works is on the call side, you just call Fibonacci. It gives you this generator. Then the first time you call it, it goes to the first co-yield result. It returns from there the integer and the handle to the function. And then you can resume, go back into it, and use the current state of the function to continue running. Yeah, that's a new way of thinking about programming because you can now have functions that keep their state alive. This also means this thing is not going to create stack memory, but it's actually going to get allocated on the heap when it actually runs. So it's a function call stack that gets created on the heap and stays alive on the heap. And here on the bottom, you now see how this thing could simply be used. So this would be, of course, because while true, this would be generating you all the Fibonacci numbers. We have to take a finite number of them. So we're using this std views take 7 in this loop down here, and we're just printing the first 7 Fibonacci numbers out. Yes, there's a question.
If you were to call that for loop again underneath that, would it start all over because you're instantiating a new?
Yes.
But you could also auto Fibonacci, like have an object that you could put in there. And
Yes.
Then, and then
you can reuse a generator, or you just, in this case, you would create a new generator. Every time that you call Fibonacci, you get a new generator. And then you have to, that the state of that generator is whatever you left it at. Yes. This is going to be actually optimized away in most cases. In the cases where the compiler decides that it shouldn't optimize away or it can't be optimized away, you will, of course, have to use heap memory in the cases that you want to go back there. So it may have some performance implication in these cases, but it also allows you to be drastically more simple in various implementations, for example, of asynchronous code, right? Where you have, you're triggering a call of a function that has to do some work, you want to get back to it, you want to do something else that the function run, and once it's finished, you want to go and fetch the result of that function. There's, for example, like if you go back to, I forgot which year it was, there was a very nice talk at CPPCon where someone used that to work around the fact that when you do a lot of random memory access, you have to wait a lot for the memory to actually arrive in cache. So what he did, he just issued a lot of prefetch operations, right, to tell it, please start fetching that memory for me. Went back to the main thread, he was just doing something useful along the lines, and then once the memory has arrived, start doing actually working on the memory. So you can start hiding the latency of fetching memory into caches with this technology super easily. Yeah.
So if this is all allocated on the stack, how do you
What do you mean?
sorry,
what is
on the heap?
The variables get like it creates a given size on
Okay. So
I wouldn't think so much about. I think in the end, the performance implications generally for simpler examples are certainly going to be non-existent because the compiler optimizes it away anyways. And if you're doing a lot of work, then generally you're spending so much time in the function that the things will anyways be in cache already. Right, I think I wouldn't think about this so much as a performance hit. I think this is going to,
I was more worried about memory leaks.
No, it's taking care. As soon as the generator goes out of scope, the stack, the part on the heap is automatically deallocated, right? So in some sense, the generator here is keeping track of the memory allocation and deallocation of the respective memory region on the heap. Yes.
I should think of this like it's basically a class with, it's a function with private memory.
Yep.
Okay.
And this is only one way to use it. This is the co-yield keyword. There's other keywords such as co-return and co-await that allow you to do actual asynchronous programming. I won't have time to go into that, but that may be a topic of like an advanced Cyware or something that we could maybe do at some point. That's going to be interesting, I think, because using that in scientific code can make some algorithms so much easier to implement. Yeah. Okay. Yes, sorry. That concludes the part on the coroutines. There is another question. Yes.
The state is not. What if I don't return the complete state for the function? Will the compiler complain or?
No. No, it won't. But it's not even clear what complete means in this case. This is an infinite series. While true.
No, what if I needed another variable in there, but I only return B? Is there a way to detect that?
I think I don't understand.
The compiler.
In where? If you were to define it up here, another variable?
Yeah, that I need to keep track of the state inside.
It's not a problem. You can define as many big objects there as you like. And the compiler will take care of deallocating all of them when the generator gets destroyed.
Talk on coroutines if you ever did one, because like I don't, C++ coroutines are so confusing to me. So I'd love a talk on them.
I think it's still confusing to many people because there is no library support. The problem is what they had actually to do to make this possible is they had to first change the language to introduce these keywords here that if you look at the way to use them, yes, it's not easy to start working at the level of these guys. But the standard library support is going to, like the STD generator, for example, all you see is the co-yield. You don't see anything else, right? And you can just start looping over the guy. It's very easy for someone to write a generator. You don't have to understand all the details that go on under the hood inside the generator object itself. So you really want to start, that's why I'm suggesting for the moment to start using the Coro support library, and things are going to get much easier with that, as opposed to trying to do everything yourself. Don't open that box. Yeah. Okay. That brings us to compile time programming with an example that I want you to read and tell me what's wrong. We can get an answer. Someone sees the problem. Yeah.
It doesn't know how big to make the array.
Yeah.
If that's allocated on the stack, it needs to know how big the stack frame is.
Yeah, it's a statically sized array, right? It means you need to pass in the information on how big this guy is at compile time. So fn here is a runtime variable. If this actually executes at runtime, how should the compiler know how big to make this guy? So that doesn't work. But I should know the standard at which the word was introduced, maybe 17, in fact, I think. It is very simple to define code that can be executed and that you can actually force to execute at compile time. And there is a keyword for that, const expression, that allows you to make this function both runtime and compile time viable. Of course, that will require that all the things inside are also compatible with that, but in this case, that's certainly the case. And then you can define a compile time constant, fn, that's just the vectorial of 5, and you can use that to define your statically sized array. So meaning that calculation and the execution of that function actually happens when you compile your code. That's something to think about. And you can do more complicated calculations that you actually do when you compile your code. For example, some lookup table or some symmetrization of a tensor, or there's many things that you could think about where it would be useful to do that once and for all in the beginning, to hard code that into your binary and to not have to do that again. Yeah.
You mentioned that const expr makes your function both compile time and runtime runnable, quote unquote.
Yes.
Is there a way to force compile time evaluation? Because if I just call this function the way you did on the slide, does this happen? Am I guaranteed for this to happen one way or the other?
Well, here it has to be compile time because that variable is a compile time variable, right? But otherwise, there is now additional keywords const eval and const init that you can use to enforce certain behavior. Yes.
It seems confusing to me that in the function signature, it's const expr type, but in the definition of fn there, it's type const expr.
And what? Ah, okay, you can turn this around. This is, yeah, sorry. This can be turned around. This is arbitrary. Yeah, it's good to be coherent when it comes to that.
Sorry, can you explain why the previous page doesn't work again? Maybe I'm stupid. I just don't understand.
Okay.
Fn is going to compute. We know factorial of 5 returns an int.
Yes.
So Fn is an int. So
this could be a more complicated function, okay, for the sake of this example. And then this variable here is something that when you run your program actually gets calculated, right? So you have to start your binary and it calculates this. STD array is a statically sized array, like a C-style array, where you have to give the size as a constant.
Oh, sorry, int comma size. I see. I got confused. Second thing in the
yes. Yeah. Yes, exactly. Yeah, we're making an STD array that takes the factorial of 5 as a size in this case, right? Yeah. So, yes. Okay. Then brings me to another part of compile time programming, that you can also make decisions at compile time using if. This is so-called if const expression. You know the common if, which is just going to make a runtime decision, but you can also just put that keyword with if which is going to make a decision at compile time explicitly. And it's always, this is actually enforcing it. This is always going to be happening at compile time. And in this case, I'm just defining a norm function, which takes an integer p and is going to do an implementation of the 1 norm or the 2 norm based on the integer that you give it, right? Doing what you would expect, like taking a dot and then the square root of the dot function, or in the other case, just summing all the absolute values of your thingy, what you're passing in, right? And if it's not 1 or 2, we can actually do a static assert, which this thing down here, if you pull it outside of that function, it's always going to give you a compiler error, right? Static assert of false will always break compilation. But because it lives inside the if const x per else branch, only when you actually go there at compilation is that going to give you a compiler error. Meaning the code has to be syntactically correct, but it doesn't have to compile. It's only going to compile the branch that actually applies, if that makes sense. When you give it a 1, when you give it a 2, it's not going to see the static. Effectively, what the compiler is going to do when you give it the 2, it's going to just remove this part of the code, remove this part of the code, and make the version of the function that has a single line. That's what the compiler is doing for you. P has to be known at compile time. Every template parameter has to be known at compile time. That's forced, yes.
Since compile time is guaranteed, is there a way to make some decisions inside based on the type of some compile time known things?
Yeah. You could check if it's a double, do this. If it's an integer, do this. If it's a complex, do this. It's actually very common to make these kind of dispatches based on the type. Very good. One example, one way that we can actually simplify that function, and that's another keyword that was introduced together with the concepts extension to the language, is the so-called requires keyword that allows you to compile time assert certain conditions outside the function. So we have just removed this part here at the bottom, the static assert, and we have pulled it out into this requires clause here at the back of the function, which is just going to make a compile time requirement that p be greater than 0 and less than 3. And the compiler, if you try to give it something larger, is immediately going to put you to that line, not even looking at the function, what the function internally is doing, and just telling you p is out of bounds. You should be doing something else here. This is a compile time decision, not a runtime decision. Yeah.
Functions based on different requirements?
Yes. Yes. If you define templates that are not ambiguous in some sense, then you can make multiple templates with different requirements. Effectively, it's part of the template signature if you want. The requirement is. Yeah. Very good. So this function is still not perfect, right? It takes any v and then just does something with the v. So what happens when you pass this guy a string, or if you pass this guy something that shouldn't go in there? What is it going to do? It's going to try to just execute the code inside and pass the type inside and maybe give you some fairly complicated error message that this function isn't callable, or it actually may go into the implementation of your type and generate error messages that are almost unreadable in some cases and can be quite lengthy. That's why it's actually good to try to protect already at the level of the function signature what can go into the function. And it also signals, in fact, the intent of the person writing the function, what you want to go in, right? Otherwise, it's very hard for you to understand. Of course, you could write it in the documentation, and you should write it in the documentation, but it would also be good to see it from the signature itself, what can go into this function. And this is where concepts come in, which allow you to effectively constrain types or do checking on types. So in this case, for example, what would we want? We would want something like a vector to go into the function to take a norm of the vector, right? And one way of describing the abstraction of what is a vector, as opposed to just saying it has to be std vector, it could be some other vector, right? You could say, what do you want a vector to be? A vector should have a size which should be of type size t, for example, or some other integer type. We could make it more flexible. And you should be able to access into it with an integer, v of 0, for example. That should be a valid expression. And the compiler will use this recipe right here now to check your types and you can get a true or a false out of it. Right here, we're just doing a static assert, for example, that the vector concept applies to a std vector of int, and that will pass. It's not going to fail. That's the way that you're going to check if a type is applicable. And the syntax that you now use in order to constrain your function looks like this. So this is the same concept that we defined before. We can just simply put the word or the concept in front of the auto keyword, which is going to say this thing here is a norm, which takes an automatically deduced type that fulfills the vector concept. And now, as soon as you pass in anything that violates that concept, you're going to get immediately a very nice error message on this line here. And also it tells the user or the person only reading the signature of your function what is your intent, which is very clean. Very good. We have more on concepts in the Scyware that we actually did on modern C++ that was recorded. There's the material online that you can find. That was session 25. There's a Vimeo with the typical Flatiron password if you want to see the video. Olivier gave a nice talk on how to use that to do lazy expressions with matrices. And I recommend all of you that want to see a few more details on this to go and look at that Scyware video. Okay, I'm already more over time than I had hoped. I will use the final time to just give some materials that I think are useful to follow up on this. And if you want to further research and start using C++ yourself in a modern flavor, as I mentioned before, it's pretty important to use the right material to teach yourself the language and to not learn old ways of doing things, right? These books, both in the latest version, the 3rd edition of this one and the 2nd edition of this one, have C++ 23 inside. And I recommend very much reading up on the latest things in either of these 2 books. A very useful page that's always up to date is CPP reference. This is the page I recommend for looking up anything on the standard library, on the language itself. It's a really, really good and clearly written reference documentation. On the side, maybe just a brief word on the side of compiling code with a modern standard. Mostly what you will need to do is you have to add an additional flag that enables the standard that you want to use. Both for GCC and Clang, it's going to be the same. You have to put -std equals C++ 23, which is of course not going to work with GCC 4.8, but you have to use something more recent than that. But yeah. And it's going to be, in some cases, not, you need to figure out if a certain feature is actually supported by a given compiler version. CPP reference also has a really nice and complete and always up-to-date table that tells you which compiler supports which feature and which standard library version supports which feature. It's really nice to look things up. And they also, yeah. I think this was already introduced this morning. Godbolt has a web compiler where you have all the latest versions of the mainstream compilers available to you to just try things out. Where you can just put your code, choose the compiler version, put your flags, run the code. I use it very frequently. It's very, very useful. Yeah, and you can share the code samples too, right? You can create short links and just share code snippets with people, and then have someone edit something. That's very, very useful. I will put the slides. We will share the slides in some form, right, for FWAM. I will put this up for people that want to have a look at these following 2 slides. This is just what we at CCQ, or specifically for Trix, are using as a typical ecosystem for development. There's a number of tools usually that go with the C++ language that are also pretty important to enforce the modern standard. Writing these down here. Not going to go into much more detail on this part. And I will leave you and end my talk with the resource slide on the other things that are great to connect and see what's going on in the C++ ecosystem with some podcasts, news sites, YouTube channels that I value quite a bit, and cheat sheets. Yeah.
Great, fantastic. Any quick questions before we all go drink?
One quick one is in terms of like how to read the concepts. You wrote like v of 0. Is the way to read that to say this should compile? Like it's saying you should be able to write this.
This should be a valid statement. You can make constraints and say this should also return something specifically if you wanted. The way I was writing it now was just saying this just needs to be a valid statement. Yeah, or expression.
Another question. As an outlook, what's the status on modules? Is there any news on this?
Oh yeah. Modules I have not been focusing quite so much on because I think it doesn't have the largest impact on scientific software development unless you're decoding your own bigger libraries. I think the biggest impact it's going to have, you're going to be able to drastically reduce your includes. Like for example, if you have been using the standard library, there is almost a header for every individual thing, right? You will just be able to write import std. It's as simple as that. And you can drop all your includes for any standard library files, just import std, and you have everything that comes with the standard library. And it will be much, much quicker than if you were to include every single header, because it's in a pre-parsed way. In some way, the module doesn't just contain the source code, but it contains it in a different format.
But the question is it implemented yet, or will it be soon?
Not in the latest. Import std you can't yet use for either GCC or Clang, unfortunately, but I think very soon, and I know they're working on it. Yeah.
Any?
For like 6 years.
It's also a complicated. It's quite a deep change to the language if you think about it, right?
It is, and I think this is going to number like Fortran mod files, which has been an absolute effing disaster in my opinion. So I'm not as optimistic as Nils is about this.
That it's going to happen. Actually, MSVC has it already today. So if you use the Microsoft Visual Studio compiler, you can use import std.